I'm happy to introduce the first talk from Professor Klara Nahrstedt of UIUC Computer Science.
Hi, my name is Klara Nahrstedt. I am faculty in the Computer Science Department at the University of Illinois Urbana-Champaign and director of the Cognitive Science Laboratory. Today, I'm going to be presenting the data management framework for scientific laboratories, which is a joint work with my collaborators at the Holoniak Micro-Nanotechnology Laboratory, as well as Cognitive Science Lab. So what is the main problem? I would like to talk about the demands of the scientific laboratories with respect to their data management. And then we will dive briefly into the instrument-based data management systems such as FORSEED, provenance-based data management systems such as Provlet, and room-based data management system like SENSELET. And I will conclude with lessons learned. We are looking at laboratories that have many scientific instruments, such as microscopes, and they really shed a lot of data. And they are network connected to provide in real time data to the particular researchers that are looking either at development of new materials or new semiconductor fabrication devices. They are shedding a lot of data, and their ultimate goal from this particular instrument is to provide digital data acquisition, curation, and sharing prior to scientific publication via sort of private cloud storage facility, and store a lot of data, including images, various metadata, and notes. So the current status is that a lot of data includes these images, like from the scanning electronic microscope, temperature information that the material, for example, was created under, oxidation depth, and other image setting of the instrument. And all this data is stored in multiple text and image files for a single instrument. Another really important issue is that it's not just a single instrument. In semiconductor fabrication, often one uses many different instruments, from profilometry to scanning electronic microscope to do diffusions, to oxidation and lithography, again, to use more optical microscopy to actually get the device characterization via SPA. So one acquires huge amount of data between these different instruments until the experiment is ending, from images to optical images to graphs to animations. And all of these particular data get then stored in the past in the file explorer, where you can see actually a lot of the data are having very long names, and the names actually include all of the metadata under which this experiment has been running. So we have worked on instrument-based data management via the system called FORSEED that uses underlying actually Clowder. That's why we are talking about it. FORSEED actually allows the instrument in the Material Research Lab, or here Holoniak Micro-Nanotechnology Lab, to connect the data that they are producing to a FORSEED private cloud. And one can also then access the particular data from the office. So what we actually allow with FORSEED, much simpler file names, automatic note taking, and also all metadata are included that are also hidden inside of the images. There is also direct web interface where you can, in secure manner, actually access the data. You can transport via web interfaces large amount of data to a secure FORSEED backend private cloud. And you can, in real time, access it from your laptop, your computer, anywhere on the campus, and also your collaborators can access the data. So just to give you an overview overall, in each of these labs on our campus, there are many different instruments. They get connected to a private four-seat cloud. And there, basically, then the data being accessed by curators to process, coordinate, store them, correlate them. The underlying system, that data management system, is the Clowder that allows us to organize all of the images, the metadata, into spaces, data collections, and data sets. And the researchers actually get a very nice and simple interface where they can actually look at their etching experiment. They know who that particular experiment was running by, when it was created, the data that currently belongs to that particular instrument, like the images, and one can also tag the particular experiment and specify collaborators. And all of the data, metadata, data, are together stored within the data sets and the data collections and organized in the hierarchy. And so one can then really see an owner can set up a space, and then basically the space will have different collections, different experiments. Within experiments, one can have different data sets with all the information that happened during that particular experiment. And one can also then share all the collections and the space with other users and collaborators. We are also very interested in this four-seat system to track who currently originated this particular data, and who currently is editing the data, who is currently accessing the data. So for this particular purpose, we have actually created the system called Provlet that will actually be monitoring the entity who is currently accessing the data, so the user, but also activity currently, when the particular process ended, that is processing currently extraction of metadata, and who is currently moving the data, deleting the data, and so on. And that particular provenance data around all the data and operations of the four-seat system are then being stored in the Provlet data-related log, but we also are monitoring via Provlet network what happened as the data are moving from the instrument to the private cloud, or between the curator, the person in the office, and the private cloud. So the network logs are being stored as well. And then actually one can visualize the various data and operations that happen to what particular users have been accessing the data, who created the data, who added, removed the tags, the files in the data sets, and they are all basically stored in a JSON-like format. And you can then visualize it. You can then sort of see basically the progression, what happens that over your particular data. The one other important aspect of data within the scientific labs is that we also need to understand what's happened around the instrument, not just inside of the instruments, as the instruments are of different ages and are therefore responsible for different fidelity of the particular data. So one can basically see if there is a bad humidity inside of the room where the instrument is. One can, instead of creating a nice smooth lines, one can create really bad type of images because the room was too humid, was too hot. And so having sensors in the room and monitoring what is happening in the room is just very important. And having an automatic data logging of these lab environments to actually understand what happens around furnaces through the temperature sensor, what happens around gas holders through the gas flow sensors is really, really important. So we have created a system called SENSELET that does actually place various sensors around this particular equipment in scientific laboratories, and then through the edge devices, Raspberry Pis, it monitors the data and stores them in the SENSECLOUD in a time-sensitive and time-series database cloud, private cloud, as well as it forwards it to the four-seat to correlate it with the instrument data. And then lab managers or researchers can view this particular data. So the function that we currently provide is tracking temperature, humidity, and then send them to the central cloud server. We also make sure that the data is reliably sensed so that one can recover from failure if needed. And this particular SENSECLOUD then stores the data in the time series database from which then one can start to retrieve it and visualize it. And we use again Grafana to have a dashboard and monitor in real time historical data or the real time data, and also send in alerts. So then in summary, we are currently using Clowder very deliberately to store data coming from instruments, as well as we forward and correlate room-based sensor data measured by SENSELET to the FORSEED to correlate instrument and room data. But also we are monitoring the Clowder data via our Provet systems to track the origin of the data, access of the data, operations of the data. And so Clowder, this is a workshop on Clowder, presents a strong backend for scientific labs and their data management. Thank you for listening.
Thank you very much again to Professor Nahrstedt.
I want to make some sort of comments
Yes.
with respect to some of the semantics of the various metadata. This is one of the major concerns to NIST and other sort of standardization bodies in the materials and semiconductor industry, that the naming of many of the metadata data is non-uniform, it's diverse. A chemist working on materials might have very different naming for the same behavior than an electrical engineer who works on microscopes. Very often, some of the naming is driven by the companies like Siemens, Carl Zeiss, that names their metadata, how to call temperature, how to call humidity, how to call certain things. And so the researchers then that work on various instruments, take the names that the companies that are providing the instruments use those particular names, but then also they give their own names to make it sense to their own processes or research that they are doing. And so there is currently a organization called MARDA that is very specific to digital materials. And this is currently an organization driven by NIST as well as by national laboratories that work with different instruments to develop materials, to develop semiconductor chips, to somehow unify the semantics, the naming of many of the metadata, very similar to what NIH and health and bio domains actually achieved. But this is just starting, and hopefully at some point this sort of more uniform naming of a lot of the semantic information around these instruments get solved in this domain. But I was actually very struck that even between material scientists, chemists, physicists using SEM and semiconductors using NMNTL had very different naming. Now, we created in FORSEED templates where people can actually provide name and then basically their values as they are running experiments so that they can then retrieve things based on their own naming. And as I mentioned, that's stored in JSON. But this whole aspect of naming and semantics is a big problem in this particular domain. It might be that in other scientific domain this is solved. As I said, we follow the NIH naming problem space, and there is a much more uniformity than it's in the materials and semiconductor space.
Thank you. I see a follow-up question from Donnie Winston, expanding on this, and maybe you've addressed this a little already, but from the slides for Provlet, it looks like the W3C Prov vocabulary might have been used, though I didn't see that in the JSON examples. Would like to hear more about that.
Yep. So I think I have Dr. Moini, who is working with me on the Provlet. Hesam, do you want to address this particular question?
Right. So we use the Prov-O, the ontology that the W3C introduces, to convert and translate the JSON-like log files to the provenance graph, and then we do a subsequent mining on those graphs to use that in different applications, such as anomaly detections and resource allocation, basically to do maybe caching for data closer to the researchers that are frequently using those data. Yeah, the provenance graph would follow the basic architecture introduced by W3C, and then we have a table-driven data structure to efficiently store that sparse provenance graph and use it for further applications. Does it answer your question?
Thank you, Hesam. Yep, looks like that's a positive there. Donnie also thanks you for highlighting MARTA, Professor Nahrstedt. If there are no further questions, thank you again for your presentation, and to both of you for your thoughtful answers.